So that's what you want to do in practice. That's a refrigerator. Okay. All right, let's look at this. All right, so of course you're not using water. You're using some kind of a coolant, okay, or yeah, so you're using, okay, so, and all this, that fluid is flowing in a closed pipe. So in here, in this pipe which is inside the refrigerator, again, it's a closed pipe, the coolant is evaporated. When the coolant evaporates, it absorbs heat from the inside. And then you bring that vapors out, and then you turn it into a fluid, and it dumps out all the heat. Okay. So you take a coolant, evaporate it inside, it absorbs heat, bring it outside, and then turn the vapors into a liquid, and it dumps the heat out. So it's that simple process. What?
It's slowly heating your house.
Yeah. So, and heat pump in the winter, this pipe would be outside, would absorb heat from the outside, and this would be the inside of your house. And you turn the vapors into liquid inside your house, and the heat is dumped into your house, inside your house. That's a heat pump. Okay. In an air conditioner, what do? This is inside your house. You absorb heat, and this is outside your house. That compressor is outside your house. You're dumping it outside. All right. Again, so to transport heat against its wishes, against its natural wishes, what you have to employ is a liquid, and you're vaporizing it where you want to absorb heat, and you're condensing it where you want to dump the heat. Okay. Again, so here's the principle. When a liquid vaporizes, it absorbs heat, and then when the vapors condense, you dump the heat. Okay. So did you guys understand that? So here's the process. So here's the engineering part of it. Okay, so here's a cool fluid, the evaporator, and then you vaporize it. How do you vaporize it? You connect it to a vacuum. So if you suck the air out, the liquid will evaporate more easily. You absorb heat, and then you have vapors, and then you compress it and liquefy it. Okay, so this becomes a high pressure vapor, and then loses heat and becomes a warm fluid, and then you cool this fluid by passing it through an expansion valve, and then pass this cool fluid there. Okay.
So what is vaporizing? So when the cool fluid goes in, and it needs heat to cool.
No. Here's a cool fluid, the coolant, and you have to vaporize this fluid. So here, in this room, do you know what the humidity is in this room? Huh? 50%. Very good, 50%. Okay. What that means is there's only 50% of water vapor, 50% of the maximum water vapor that can be held in this room. Okay, so right now, if you had an open cup of water vapor, more vapors would evaporate. And now if you hook this to a vacuum pump, more vapor would evaporate. More evaporation would happen. And so heat would be absorbed. The more evaporation happens. And that's what you're doing here. So here's the liquid, coolant liquid. And if you hook this to a pump, as it sucks the air out, more of the liquid will evaporate and more heat is absorbed. Okay. Now, the deal is the following. So, how do you choose a coolant? Okay. So if you want a refrigerator where you want to maintain a temperature of minus 20 degrees Celsius, the boiling point of this coolant has to be below that. Okay, that's how you decide what coolant you have. So if you want minus 20 degrees, the boiling point of the coolant better be minus 25 degrees Celsius. The temperature inside your refrigerator is 4 degrees. In your freezer, it's about minus 5 degrees, and so on. Anyway, air conditioners and refrigerators are heat pumps as well. Again, what is a heat pump? What is a heat pump? It takes heat pumps heat from a colder region to a hotter region. All right, so what does a refrigerator do? It absorbs heat from a cold temperature and dumps it into a hot region. Okay. Well, it just won't do that. You have to do work to be able to do that. Soon as you stop doing work, this process stops, because nature wants to do this. Okay. Nature on its own will do this, but if you want to make it do this, then you have to put in work. Okay. So we define a coefficient of performance. The coefficient of performance is how much heat you remove from the cold region. That's what you're interested in. And what was the price you paid? How much work did you have to do? Okay. And for an ideal refrigerator, again, this is an upper limit, just like the Carnot engine. The coefficient of performance just depends on the temperature. Again, these are in the Kelvin scale. Okay, so it just depends on the temperature. So typical household refrigerators, the coefficient of performance is 5. Yes.
I don't know, I remember we were talking about good versus not.
I believe you have better ones than this, okay? So let's see. So let's see, what does this number mean? You remove 5 joules of heat from your refrigerator for every joule of work you've done. Okay. One and 3. All right, there you go. I guess I lied in my notes. All right. Okay, the next few slides, what I'm going to do is we're going to comment on this guy. Here's how you calculate. If you wanted to calculate the entropy for a given state, this is the formula you would use. That's a Boltzmann's constant. That's the number of microstates for a given macro state. Okay? Now I'll tell you a couple of things that are important in statistical mechanics and give you an example. Okay? So we'll do a simple example. Let's say we've divided this room into these slots, and you can put molecules on only these slots. Okay. So the question is the following. Okay, so you put a gas in this room, and the gas is evenly distributed everywhere. If you measure the density of gas, it's constant throughout the room. So the question is the following. Why doesn't the gas all come to one side of the room? Is this even possible? is this distribution possible? I mean, the total energy hasn't changed. All I'm asking for is all the gases to come here. You know? Heck, I mean, you guys walk in, you randomly sit everywhere. You never sit all on one side. Right? All right, so why doesn't that happen? Okay, so here's the fundamental law of thermodynamics. It says the system will spend equal time in every macro state. It doesn't, it doesn't prefer one microstate. Okay, it's just that. So, so with all the gas in this half of the room, all the gas in this half of the room. So let's say you have 10 molecules. There's only so many ways to distribute them. Okay, but if you could distribute them through the entire room, there would be so many more ways of distributing them. Okay, so now I'm just going to make some number up. All right, it's not impossible. But are you going to be able to see it in your life? No. So that's the punchline. Did you guys understand that? Okay, so I'll show you a simple calculation. Okay? And that's the important thing. Okay, so that's important. What is the probability of finding all the gas molecules in one half of the room? Okay, what you're going to take is you're going to take only 100 molecules. How many molecules are there in this room? Very good, 10 to the 28. What happened, David? You weren't listening? All right, 10 to the power. So this is with 100 molecules. Okay, what is the probability of a single molecule being in this room? The probability is a half. What is the probability of 2 molecules being in this half of the room? Half times half. What is the probability of n molecules being in this room? Half times to n times. Okay. If you calculate for 100 gas molecules, 1/2 to the power 100 is 10 to the power of minus 30. What that statement is saying is, if the probability of the gas being spread evenly is 1, the relative probability of only 100 molecules being in this half is 10 to the minus 30. For every second of evenly distributed, all the molecules will be in this half for 10 to the minus 30 seconds. That's the statement. This is for just 100 molecules. For 10 to the power of 28 molecules, that number would be even tiny. Okay? So for 100 molecules, if the system spent 1 second per microstate, this would take about 10 to the 22 years. Okay, so what that means is in 10 to the 22 years of the molecules being evenly spread, 1 second will be spent here. And that's what it translates. And 10 to the power of 22 years is, how old is the universe? How old is the universe? 13 billion years. 10 to the 10 years. That's how old the universe is. This is 1 trillion times the age of the universe. Okay, so again, if you had 100 molecules in this room, for 1 second in 1 trillion times the age of the universe, you'd find all the 100 molecules here. That's how small the probability is. So even though that's possible, you'll never see it. Okay? And that's why you don't care where you sit, you know. You're not worried about all the air coming on this side of the room. Okay? All right, so that's what this is saying. See, when you see the temperature in this room that is evenly distributed, the pressure in this room is evenly distributed, pressure and density, everything is even. That's because that even distribution has so many more microstates than the uneven distribution. Okay, so that's why you. Okay, so in equilibrium you'll always see what you see. I mean, that's the reason why you see what you see. Okay, so for this, the number of microstates is that. For this, the number of microstate is 0 compared to that. All right, this goes through a derivation. We won't worry about that. Okay, so here's how you calculate the entropy. Entropy for a given macro state. So entropy for a given macro state is S equal to K log W, where W is the number of microstates, number of compatible microstates. Okay, so when you want to calculate the entropy of a black hole, that's what Mr. Hawking was doing. Okay? Hawking and other people. He calculated the number of microstates. All right, what was the Carnot engine? Okay, all heat engines go through a cycle. A Carnot engine was an ideal heat engine. This was isotherm, this was isotherm, this is an adiabatic, and this is an adiabatic curve. The Otto cycle, this is an Otto cycle. It's the modern internal combustion engine. So the air-fuel mixture in your car goes through this cycle. This is an adiabatic isochoric process, and adiabatic process. This is charging or recharging. Okay, so you put air-fuel mixture. No, you put air-fuel mixture. This is you're putting in air-fuel mixture as the cylinder is expanding. Then you compress it, you light it. Then this is the power stroke. This is when the work is being done. Then you're exhausting it. No. And then you start exhausting it. And then back recharging, compress, light, work, and again, and starting to discharge. Okay. So that's the Otto cycle. A real heat engine is based on it's not based on this. This is the Carnot cycle. So intake stroke 0 to 1. Intake stroke, you're taking in air-fuel mixture. Intake valve closes, compression stroke, fuel air ignition, power stroke, exhaust valve opens, and then exhaust stroke. Okay, so that's what you're doing. The efficiency of your engine is 1 minus R. R is the compression ratio. V1 to V2, how much you compressed. Okay, so you see, and gamma is the ratio of specific heat. So air-fuel mixture is for gamma, it's probably less than 1.4. Okay, so anyway, less than 1.4. Well, it's greater than 1. So this is efficiency is 1 minus 1 over R to the power gamma minus 1. Okay. Greater your compression ratio, higher your efficiency. Greater the compression ratio, what is that you have to deal with? Pre-knocking. Okay. So premature ignition of fuel. Okay. So anyway, that's okay. So efficiency of your engine should be 60%, but for your real engine, but it's about 30%. Okay. And this very high compression ratio puts high stresses on components of engine. The actual gasoline-powered internal combustion engine, the compression ratio ranges from 8 to 12. if the compression ratio is too high, the fuel-air mixture will detonate before the compression is complete. Okay. That's the pre-knocking that we talk about. You can read all those. Okay, diesel engine. So diesel engine, what you do is you take in air, compress the air. It's not air-fuel mixture, you're just compressing air, which warms up, and then you insert fuel, and that fuel lights up. And when you insert fuel, you don't need a spark plug. Why does the fuel light up?
Because the air is so hot.
And the air is so hot, okay? So all you have to do is put in, you fuel in the hot air, and it lights up, okay? The fuel is introduced between 0.2 and 3 only after the air has been compressed. The thermal energy of the compression ignites the mixture, okay? Again, since you don't have pre-knocking, you can try and compress the air as much as possible, okay? So diesel engines are more efficient, okay? Okay, so the efficiency of a diesel engine is 1, again, that's the compression ratio, and alpha is V3 over V2. It's the ratio of the final and initial volumes in the combustion phase. This alpha is this ratio, V3 over V2. Okay. Anyway, diesel engines are more efficient than internal combustion engines. Okay, so diesel engines get around the problem of pre-knocking, yeah, pre-ignition.